Momentum integral estimates. When we derived the momentum integral in chapter 7 from the governing equation on the fluid flow and apply it to a flat plate boundary layer before, we promised to consider it further in this chapter. Let us review the picture for momentum integral on a flat plate. Consider this picture. The no-slip wall condition retards the flow, making it into a rounded profile UXY as shown in this picture. So we have a steep profile, rounded profile UXY, rounded velocity profile. Which merges into the external velocity u equals to constant at thickness delta x. By utilizing the control volume, we can find that the drag force on the plate is given that the following momentum integral across the exit plate. Write drag force dx as a function of x is local drag force, rho the width of the plate, integration from 0 to delta x. Delta x is this point, for example. When we want to integration, we have to integrate from this point to this point. In this case, we have dy, where b is the plate width into the paper, and the integration is carried out along a vertical plane x constant. So for more explanation, there are various solutions for the drag force. Drag force from on the immersed flat plate. The first approximation and solution is Kármán's analysis of the flat plate. This equation was derived in 1921 by Kármán, who wrote it a convenient form of momentum thickness delta. Let me define as momentum theta where the x from Kármán analysis is rho b u square theta, where theta has a relation as dy. Momentum thickness is thus a measure of total plate drag. Kármán then noted that the drag also equals to the integrated wall shear stress along the plate dx direction of shear stress tau wall in x direction. Or we can write d dx on dx and u is constant. Meanwhile, the derivative of the equation of Kármán with the constant u gives us the differential form of relation for drag force, which is dx rho b u to the derivation of theta on x. By comparing this equation with the equation of Kármán, arrive at what is now called the momentum integral relation. It gives us a relation for the shear stress on wall It is valid for either laminar or turbulent flat plate. To get the numerical result for laminar flow, Kármán assumed that the velocity profile has an approximately parabolic shape. So Kármán approximately, let me write Kármán's velocity profile. Which is U which make it possible to estimate both momentum thickness and wall shear stress. Theta equals to the we have a relation for theta which was U on U, in this case theta Y on U on U minus dy. So the shear wall can be calculated as also this relation at 0, which can obtain the Kármán's velocity profile and calculation for theta and also for shear wall stress. By substituting to the previous equation, especially to equation of the shear stress which obtained before here, we can derive a relation between the boundary layer thickness and flow and fluid specification, which give us delta for example the kinematic viscosity u on dx. We can integrate it from 0 to x, assuming that delta 0 at x, delta 0 at x0. So we can, with integration, we can obtain this relation for the thickness of boundary layer in a flat plate due to the Kármán assumption. This is desired thickness estimate. It is all approximate or of course part of Kármán's momentum integral theory, but it is startlingly accurate, being only 10% higher than the non-accepted solution for laminar plate flow, which we gave in the previous section. And now we can also calculate the shear stress estimate along the plate with the relation CF Reynolds X Again, this estimate, in spite of the crudeness of the profile assumption, Kármán assumption, is only 10% higher than the non-exact laminar plate flow solution, which was CF, coefficient of force. Laminar flow. In this case, the dimensionless CF is the skin friction coefficient. It is analogous to the friction factor F. A boundary layer can be judged as thin if, say, the ratio delta on x is less than about 0.1. So for thin layer, layer of boundary layer assumption, we can assume that delta on x is smaller than 1/10. This occurs at 4 delta x on Reynolds or at with this Reynolds x 2500. For Reynolds x less than this quantity, we can estimate that boundary layer theory fails because so for this inequality, boundary layer theory fails. Because the thick layer has a significant effect on the outer viscid flow. The upper limit of Reynolds for the laminar flow is the limit for a flat plate upward. The turbulent Reynolds number may be arbitrarily large, and a practical limit at present is, and for this is for laminar, which we write here, and for turbulent, the upper limit is Reynolds much bigger quantity of Reynolds number for turbulent flow. The next